Okay, so here's what we were talking about last time. We just sort of barely started the chain rule, and let me just remind you where that comes from. We already talked about this idea here. This is, different notation, I suppose, but this is our formula for a linear approximation, right? The change in the output is going to be computed by this formula that we talked about and motivated previously. So the observation is, if you look at this as, well, we got a function from R2 to R1, the variables being x, y, and z. In other words, here's a sort of a little diagram of what this is a picture of, right? If you then say, well, now let's suppose x and y are functions of t. So we're precomposing here. On the left, you might say, you're saying, sure, z is a function of x and y, but x and y now are functions of t. Then you can talk about, well, what about the composition? How is z a function of t, sort of, through x and y is kind of now intermediate variables in between the input t and the output z. What is dz dt? And a real easy way to get to that is just take that green equation and just divide by dt, and there you go, right? There's your formula. Here's your, the partials of z with respect to x and y, what you might call the green derivatives, are there. The derivatives of x and y with respect to t, the blue derivatives, you might say, are there, right? We have a formula for how to use the derivatives of individual functions to conclude the derivative of the composition, which is what the chain rule was in a Calc 1 context. So what we have here is our sort of first instance of a multivariable chain rule. Okay. All right, so that's where we left off last time. I want to spend a couple of minutes motivating this in a different way. I think this is intuitively pretty satisfying. This is also a really nice perspective on certain kinds of computations that we're going to be doing with the chain rule. So this is, I think, a big point. Let's kind of rewrite the functions, I'm going to say, sort of vertically. So z is a function of x and y is functions of t. So we're now going, writing the functions as going up instead of to the right. People do that sometimes. There's different motivations. You might think of this as looking more like a hierarchy, for example. Z comes from x and y, which come from t. Anyway, people write it like this sometimes. Okay, so where do all of the sort of participants in this equation show up? Specifically, if we're interested in the derivative of z with respect to t, how would that come about? I mean, just intuition-wise, forget about the fact that we already have a formula. What does it feel? I mean, how should changes in t cause changes in z? All right, well, here's a point of view you could take. You change t a little bit. This derivative right here, dx dt, tells you the factor that you would multiply by that change in t to get the corresponding change in x. Now, that's not what the question was. The question was, how does z change, right? But here's the thing. This dx dt, the factor that you multiply by a change in t to get a change in x, if you then further multiply by the factor by which changes in x should cause changes in z, right? This product altogether, that product kind of gives the combined factor along this path, you might say, that along which changes in z might propagate through x to cause changes in z. And you could view, what we've got here in this sort of dark blue path that I've just highlighted here. You might say that is kind of on its own sort of a reminiscent of how the single variable chain rule worked. Right? You multiply factors, you multiply derivatives in the chain rule because each of those derivatives is a factor, and that's how factors combine, is they multiply. Okay, so changes in t cause changes in z as propagating through x. And then we just have to make the following observation. Then it's like, well, yeah, okay, but that's, sure, but that's how x works. That's how, changes propagate through x. But that's not the only way changes in t can move. Changes in t will also simultaneously be causing changes in y. And changes in y, as a result, will cause changes in z. And again, we have sort of an additional factor here, an additional contribution. Altogether, this red path says, look, by way of y, t changes are going to cause y changes are going to cause z changes. Altogether, the product of those factors tells you how t changes are going to contribute to z changes by way of y. And the thing is, both of these things are happening at the same time, right? When you change t, that's going to change both x and y. So grand total, both of those contributions, the contributions by way of x, the contributions by way of y, both of those are going to contribute to the total amount that z changes, and thus we take the sum of those to get that derivative dz dt we were looking for. Now that's just a point of view, reasonable point of view, but I think pretty satisfying. And I think there's a lot of value. There's a lot of, again, this sort of perspective is a very convenient computational perspective to take that we're going to make big use of as we go through and do a bunch of examples. Okay. Alrighty. Moving along. Here's an example. I guess I'll leave that up. Okay, so using the variables laid out the same way that we did previously, z is a function of x and y. X and y functions of t. Let's talk about what is the derivative of z with respect to t. And so, same layout of variables as we had on the previous page. Okay, well, using this formula here, right, we need to compute individual derivatives, some of which are partial derivatives, combined per this formula, and out comes what we're interested in. So here are those individual derivatives. The derivatives of z, these are partial derivatives with respect to x and y. That's easy calculations. Again, make sure that you're good at this point with doing partial derivatives. It's pretty much all the old derivative formulas that you memorized already and are already proficient with from single variable calculus. With the added bonus, you get to pretend like large parts of the function are constant, because for the purpose of those partial derivatives, they are constant. Okay. So make sure you're good with that. Yep.
Could you also just plug in x and y?
Yeah, let me come back to that. Yeah. Okay. So yeah, you compute these. Now, the derivatives that you need on the green side, you need the derivatives of x and y as functions of t. Now, individually, x and y are just single variable functions. X is a function of t. Right, it's a Calc 1 thing. That's a plain old derivative. That's not a partial derivative. Likewise, y. So you compute those, stick them in here where they're supposed to go per the formula on the previous page. Whoops. Come on, colors. And combine, and there you go. There's your expression for that derivative. Okay, now, great question. He asks, can't I just take this formula for x and stick it in there, and take this formula for y and stick it in there, and then get z as a great big function of t, and then now I've got a Calc 1 problem, and just take a Calc 1 derivative, right? Now, that if your goal is to get a numerically correct number that you put at the bottom of the page in a box with a smiley face, okay? If that's your goal, then yes, that will get you numerically the correct answer. But two things. First of all, that is going to be, certainly in some cases, much more work. Secondly, in some cases, that's going to be inaccessible. Sometimes you simply cannot do that because maybe these functions aren't explicitly given. Maybe all you know is some of the partial derivatives, but you don't know the actual functions, right? And then also, finally, and arguably the biggest point, let me just remind y'all why we're here, right? What are we doing in this course? Our goal in this course is not to get answers. Our goal in this course is to understand ideas and concepts and tools, that kinds of thing, right? So our goal here is to understand the option of using what we call the multivariable chain rule, right? And so that's what we're talking about. The fact there is another option that will get numerically correct answers. It's just not what we're doing. It's not what we're interested in this context. Let me remind y'all now. Again, it's a great question. Let me remind you how this relates to exams. keep in mind, again, exams are not graded based on whether or not the box at the bottom of the page has the right number in it. That's simply not what we do here. That's a very high school point of view on math, right? That's not what Math 212 is. As such, one of your jobs in taking the exam, step one in looking at an exam question, is ask yourself, what's the purpose of this question? What is this question about? This instructor put this question on this exam because this instructor wants to test my proficiency with what Math 212 idea. Right? So identify what I want and give it to me is pretty much the advice that I like to give on that. Right? So I want to know what I don't care if you can get the right answer in the box at the bottom of the page. It's just not, again, it's not what we do. I want to test certain ideas. So you see a problem like this, for example, on one of my exams. There's the given, and here's the question. Find dz dt. Why would I put this question on the exam? And I think the perfectly clear answer to that question is because I want to test whether you're proficient in executing the multivariable chain rule. So give it to me. Does that make sense? Is everybody happy with that? Yeah. Now, outside of the context of Math 212. There may be some situations where it might actually be more convenient to just plug it in, make it a single variable function, and and then take a deep breath and plow. Right? That's maybe in some contexts, right? But again, we are in Math 212 right now, so you want to take a Math 212 point of view on things. Yeah. Okay. So the answer is kinda yes, but kinda no. Yeah. Okay, great, fantastic. Let's look back at this. What did we just do? We computed this derivative and this formula. There is something I will admit a little bit weird about this formula. Z is a function of t altogether. When you say dz dt, that says arguably view z as a function of t and then take the derivative. If z is a function of t, shouldn't the derivative be written as a function of t? Right? This is not an entirely bad complaint. Of course, now I'll remind you that x and y are functions of t. Right? So you might, to the question of have I written this as a function of t? Well, it kind of is. I've just sort of compactified it. Right? But furthermore, having it in a compact form, not having unnecessary cosine t's all over the place is nice. Okay. All right. Okay. So let's see here. So let's compute the value of this function. We've got dz dt. There it is. Let's plug in pi over 6. How do you plug in pi over 6 into here? Well, pi over 6, that's a value of t. So you're going to plug that in for t. And what do you do with the x's and y's? Well, it's exactly the same thing. You plug pi over 6 in for t, and then just don't forget x is a function of t, and y is a function of t. Oh, I hit the wrong one there. Oops. So now you can make this whole process much simpler by just saying, look, once you've decided that t is equal to pi over 6, plug that in just the once. Compute x and y. What are these values of x and y when t is equal to pi over 6? And once you know what x and y are, well, then you just plug in directly from that and don't sort of feel the need to plug in to the original equations several times, right? Just find the x and y once, and then plug those in across the board. Okay. All right. And then it's a matter of plug and chug. All right. Okay, so now we considered here, it's a good starting case. We considered what happens when you have what I like to call two intermediate variables. Right? So again, we have, z is a function of x and y are functions of t, and these represent two different paths through which, you might say, changes in t can contribute to changes in Z. Right, so 2 intermediate variables, 2 corresponding paths through which changes can propagate. So when the question comes up, okay, what if you have more than 2 intermediate variables? What if you have 3 intermediate variables? Well, if there were additional intermediate variables here, sorry, I wanted to change the color here. More intermediate variables, well, then you'll just have more terms because there's more paths through which changes can propagate. Would be one point of view to take. All right. So along those lines, here you go. That path gives that term. This path gives the next term, et cetera, et cetera, et cetera. And then finally, that path gives that term. Does that make sense to everybody? Pretty plausible, I think. Okay. All right. Okay. Oh, now here's another twist. What if we don't just have a bunch of intermediate variables? What if we have a bunch of different input variables? It might still remain, now as I have the picture set up here, Z is a function of a bunch of Y variables, each of which is a function of a bunch of X variables, and I might want to know the partial derivative of Z with respect to Xi. How would I deal with this situation? What do you do with all these additional input variables? Do they give you more terms, kind of like the additional intermediate variables did? And the answer is no, they don't do a thing. Hardly. Barely anything. And here's why. We're looking at a partial derivative. And if you're looking at a partial derivative, that means the very first thing you do is consider all of these variables here constants. Right? If you're considering them as constants, then it's like they basically disappear. And in fact, then this question of how do changes in that bottom variable propagate through the intermediate variables to give you changes in the top variable, exactly the same formula as before. The only difference, there is one difference, and that is that when you talk about how these sort of initial changes, changes in xi cause blah blah blah, those now become partial derivatives instead of just straight up derivatives. We called them previously straight up derivatives because there was only one initial variable. They're now partial derivatives because we are in fact holding all those other variables constant. So that's the one little difference, but in terms of the structure of the formula, it's not much difference at all. Is everybody on board? Does that seem kind of plausible? Cool. Okay. All right. So our chain rule is developing. It's getting sort of more and more sophisticated, more and more general cases, right? Let's take a pause and do an example. Suppose that we are given this question. We've got a bunch of equations given, and we've got a question. How do you compute the partial of, in this case, W with respect to Y? Okay, what I want to encourage you all to do when you see a bunch of equations like this, it will not always be the case on an exam that those equations will sort of come stratified for you. The reason we do this is because that's not how life comes, right? When you need, outside of the context of Math 212, when you're going to find yourself needing to use the chain rule, you're doing some experiment in an engineering lab, and there's all these different parameters that depend on each other in different ways. You've got to have to decide what's a function of what, and how do these things fit together, right? So the first thing you need to do is identify, what's a function of what, and make yourself what I like to call a little roadmap of dependence. So W, you can see right here, is a function of P, Q, and C. Right? P itself, that's one of the input variables there. P is a function of X and Y, and that suggests, and I need to put that down there like this. Right? And then likewise, P, Q, and C, all functions of X and Y. So something like that. So all together then, here's our roadmap. Here's which variables depend on what variables. So with this little roadmap made, you can see what we've got, and it says, a partial of W with respect to Y. There's W. There's Y. And the little diagram tells you, it does kind of the thinking for you. It tells you, W changes come from Y changes by way of these intermediate variables P, Q, and C. So those are your intermediate variables. And notice you get 3 terms, one for each intermediate variable in the usual way. Right? You've got your changes through P. You've got your changes through Q. You got your changes through C. Right? And there's your formula. And so the question now comes down to evaluating, 6 really easy partial derivatives. This I am going to, again, leave as an exercise for you guys to, again, make sure that you can do this. These formulas that you can compute these 6 quick partials, and you get this as your result. Everybody see, though, the importance of the layout and how to use how to create the diagram and then use the diagram to identify what to do. Students who don't do this make a certain very common kind of mistake, such as including on here something along the lines of, partial of W with respect to X, partial of X with respect to Y, something like that, which doesn't make any sense. That doesn't make any sense at all, right? Or instead, perhaps inadvertently forgetting that term and doing just this, which is wrong. Okay. Or worse, and I see this sometimes, some students will write down this, forget both of these terms, justify it by saying, well, hey, look, check it out, the partial P's cancel, ergo, right? Doesn't that look persuasive? I mean, they give you this argument in a single variable calculus class that, you could just cancel the differentials and, that's why the chain rule works. Well, it really doesn't work in the multivariable context. Everybody on board? Okay. And a couple of quick words as to why. I mean, and this is one of the problems with the Leibniz notation, is it makes it look like there is this thing called partial P, and that's a perfectly well-defined thing, right? And that thing is, it's not so much that that's a thing. That is a notation that represents a calculation that's done under certain assumptions. This is part of a notation that represents a calculation that's done under certain assumptions. And the thing is, the assumptions that go into this calculation are not the same as the assumptions that go into this calculation. Right? This one here, for example, that calculation there says, let's pretend that Q and C are constant. You're not doing that here. When you're computing the partial of P with respect to Y, you're not assuming that Q and C are constant. Q and C are decidedly not constant. In this calculation here, in this calculation, Y is changing. X is fixed. Q and C are almost certainly not constant there. Right? Okay, so again, the notation is really deceptive. It looks like we've got fractions, and those fractions are of ratios of well-defined individual objects. They aren't. They're just, unfortunately, they're vaguely suggestive of meanings that are vaguely true, but kind of different in different cases. So anyway, make sure not to step on that landmine. It's a common problem. Okay. All right. Let me skip down to the bottom of this page real quick. Some of y'all have seen matrix multiplication before. Show of hands real quick. How many people have seen matrix multiplication? Some, but not all. Okay, great. For those of you who haven't seen it, and as a reminder for those of you who have, I need to tell you what it means to multiply two matrices. We're just going to view this just as a computational formula right now. There's a long discussion of why is the following formula I'm about to give you a good choice to make for, what does it mean to multiply two matrices, and we just don't begin to have anywhere near enough time to have that conversation. So this is just a formula right now. If you take Math 216, I'll give you a long, I think really interesting discussion of why this is a great choice. Not going to talk about it here. So here's the formula. If you have a matrix that's the product of two other matrices, And if you want to compute an individual element of that matrix, here is the formula. I'm going to compute that AB element. You identify what row that element is in, and you take the corresponding row of the left matrix. You identify what column that element is in that you're trying to compute. You compute the corresponding column, or you look at the corresponding column of the right matrix. And then you take these two identified columns and you do their dot product. That's the formula. Now, outside of a context, it's not at all clear why we would make such a choice. This is, first time I saw this formula, I remember thinking to myself, okay, somebody made some weird stuff up here, right? And unless you've seen a good justification, I encourage you to sort of take that position. That's weird. It's hard to see why this would be a reasonable choice. And you should be skeptical and leery about this oddball choice, you know. And then I hope you'll also have a little faith that, there's a really good answer. There's a great reason. This is ultimately extremely natural in ways that we just can't talk about in this context. Anyway, that said, sure, trust us that, we've made a reasonable choice. But you should have a raised eyebrow until you see that justification. Okay, but this is the formula we're going to use as far as Math 212 is concerned. We just plug and chug with this formula. Now, with that in mind, let's go back up here, and I want to ask yet a more general case. We've talked about the case of multiple intermediate variables. What happens? You get more terms. We've talked about the case of multiple input variables. What happens? Well, not really very much, right? You're looking at partial derivatives. You just pretend they're mostly constants. Right, that was a sort of an easy one. Okay, now the next extension, let me call it that. What happens if you have multiple output variables? Well, largely the same thing. I mean, when you're taking a partial derivative, you're going to be looking at the derivative of one variable with respect to another, and there's going to be a certain number of intermediate variables, and you're going to look at the various paths. Right? And if there are other output variables, okay, I'm not computing their derivatives right now. I suppose that when I'm done computing the partial of Z1, I suppose I could subsequently just become interested in the partial of, let's say, ZP, and I could do an analogous calculation. But it's got nothing to do with the calculation of Z1. Yeah? Okay. All right. Okay, but it does allow us to bring up a really nice observation, and that is this formula that we have here. That formula that we've thought of as a sum of a bunch of terms, and that terms correspond to paths, this suggests that I can actually view this as a matrix product. And it's hard to see this coming. You just have to kind of notice the algebra. First observation I'll make, this formula, it's a dot product. Yeah? I mean, it's a sum of a bunch of products. It's got the structure of a dot product. And furthermore, it's exactly the dot product that you would get if you were to take these matrices and just multiply them as I've got them laid out here. Now let's talk about the layout, where these matrices come from. I'm going to look at this function that gives me the y's as functions of the x's, and there's a bunch of partial derivatives there. I'm going to organize them like this. The first output variable, I'm going to look at its partials in the top row. The second, etc., down to the last. Each one of those output variables I'm going to view as being a row, and the row is made up of all of its partials with respect to all of the different intermediate variables. Input variables, x1 through xn. Okay. Everybody on board? That's just a notational choice. And then something very similar for this matrix. If I want to look at how the z's are functions of the y's, I want to lay out this matrix the exact same way. I then want to view the product. Okay, well, the product says I want to think of the z's as functions of the x's. Let's temporarily ignore the y's in here. I want to view the z's as functions of the x's. And again, what I'm going to do is one at a time, I'm going to take these outputs. Each one of those outputs has a bunch of different partials with respect to all the various inputs, those being the x's. We're looking at the composition, right? Z's are functions of x's. And I'm going to, for each output, I'm going to make a row of partial derivatives. So this is just the layout. This is the structure of what we call a Jacobian matrix. The Jacobian matrix in this case, we're looking at here, this is the Jacobian of the composition. Here, let me do this. The Jacobian of the composition, where z's are functions of x's. All right. This is the Jacobian of f. That's where the z's are functions of y's. This is consistent circling. Come on. Jacobian of g says how are the y's functions of x's. Laying out the Jacobian matrices in the same pattern in the case of all three of these multivariable composed functions. Okay, so this is my claim is that when you write a Jacobian matrix in this form, as relates to functions composed in this way, the amazing thing is that all of these composition partial derivatives are computed automatically by the formula for matrix multiplication. It's the weirdest thing in the world. It just works. So, for example, let's look at this one. Partial of z1 with respect to xm. Okay, well, our old point of view on that would be to say, well, there's z1, there's xm. I've got a bunch of intermediate variables, right? y1 through yn. And I'm going to be looking at a bunch of partials of the y variables with respect to xm. Hey, look at that. That's that right column. That's the column that the partial we're trying to compute is in, per this formula. Right? And then look at this. We're going to also be computing these partials, the partials of z1 with respect to all the y variables. Oh, look at that. That's this row. That's the row that the element we're trying to compute is in. And sure enough, matrix multiplication says take that blue row, dot it with that green column, and when you take that blue row and dot it with that green column, you get exactly the formula that we've been writing down all along, which I guess I wrote back here. You get exactly this formula here. It's the exact same formula. So this is, as it turns out, a really powerful observation. Sure, you can think of the chain rule as a way to compute partial derivatives, one partial derivative at a time. Or you can think of the chain rule as a statement about how matrices full of partial derivatives relate by way of the very simple construction of matrix multiplication. This is a much more sophisticated point of view on the chain rule. Yeah.
Does it matter if the last matrix, like if we switch the
Yeah, the order matters. Yeah, unfortunately, matrix multiplication is not commutative. It's it's just, again, there's a lot to say about matrix multiplication, but sadly, it's not commutative, and you do have to do it in this order. Which, by the way, let me recognize, does seem sort of backwards, right? When you're composing the functions, let's see where I'm going to write this. Well, that one acts first and that one acts second. But the one that acts first, you write on the right. The one that acts second, you write on the left. And we're kind of accustomed to going left to right instead of right to left. So you do have to do, it looks backwards at a glance. There's a nice point of view that I'll be able to give you in just a minute as to why this is actually not backwards. This is actually as it should be. But you do have to do it in this order. Yeah. Then you just multiply by another matrix. Yep, totally. Absolutely. We're not going to do anything like that, I don't think. But rarely we might, but it's, mostly not. But yes. Okay, so different ways to think about this. One point of view you can take on this is, you know what? I like the simple formula. This is cozier and more familiar, and it's just variables, and it's a single formula, and I like this is familiar algebra. I'm going to stick with this one. Here's the problem. If you have this scenario, there are lots of different partial derivatives to talk about. You might say that there are p different z variables. There are m different x variables with respect to which you could take the derivatives of those p different z variables. You've got a bunch of different partial derivatives that you could conceivably want to compute, right? And when you're going to write down all of them, what if we have four? What if there's four of each of these things? P, N, and M are all four. You're going to write down 16 separate formulas? I guess you could, but this is a really convenient little, I like to think of this as a bookkeeping tool. It's an organizational tool for how all of these things relate in very natural ways. So, cool idea. And it's useful for more than just that. Okay, here's a great example. Now, we're going to start off to be just a special case. Again, look at our formula here. If we've got z's are functions of y's and y's are functions of x's, then you multiply the matrices in this way. Well, suppose there was only one input variable and only one output variable. Well, if there's only one input variable, then all of this goes away. There's only one x, and so there aren't a bunch of different x sub whatevers. There's just the one input variable. There's also only the one output variable. Wait a second. What am I doing here? Did I do this? Sorry. Got the wrong example. I was thinking of a different example. Okay, so we're going to consider just the case where there's just the one input variable. So all of these terms disappear because there's only one input variable. Likewise, all of these terms disappear. There aren't a bunch of different x variables with respect to which to take derivatives of z. There's just the one x variable. All right, everybody on board? This is just that special case where I guess you could say where m equals 1. And then notice, if I were to think of this input variable as being t instead of x, this becomes a derivative, like a time derivative. That becomes a time derivative. These become velocity vectors. Let's go back to the picture where I have this already set up well. Everything's a function of t. This being derivative with respect to t is a velocity vector. This being derivative with respect to t is a velocity vector. Okay, so looking at a picture then, and what I'm going to do is I'm going to try to fit all this on this. Yeah, I think I can. Here we go. Okay, so what we've got then is the x sort of world with all the x variables. We've got a velocity there in the space that has all the x variables. Then we've got this y world with all the y variables. We've got that velocity vector. This matrix, this thing that is the derivative, the matrix of all the derivatives of this multivariable function that gives the y's as functions of the x's, that then is the thing that you multiply by this velocity to get that velocity. Now it's just a special case of the matrix form of the chain rule. But it's a nice interpretation. What we have, previously, on this previous page, the Jacobian matrix was just a bookkeeping tool. It was just, was a way I don't want to write down 16 different versions of morally the same equation. This one matrix equation does all of them. for me, and that's it's less pencil lead, it's less paper, less space on the page. It was, like I say, an algebraic bookkeeping tool. Now we have a geometric interpretation of this matrix, this purple matrix here. The Jacobian matrix is the matrix that relates input velocities and output velocities. And let me remind you, one of the very first things that we were talking about derivatives, when we first started talking about multivariable derivatives, and I said, don't hang your hat on the partial derivative. The partial derivative is nice, and so it's got its convenient aspects, right? But there are more sophisticated points of view on derivative, a bunch of different kinds of derivative, and all of them have this one primary feature, and that is that there are relationships between input changes and output changes. This is an even more general version of that kind of thing than what we've seen in other contexts. If we think of, we've got this function g, and we're thinking about, given some starting point x, there's some corresponding output point y. If I were to start moving with some velocity, that's an input change. This x prime vector represents movement in the domain, how I'm changing what I'm putting into this purple g function. Multiplication by the Jacobian converts that then into the output velocity. That's the output change, the rate of change of what's coming out of this function. So the Jacobian is the relationship between the input change and the output change. Very naturally, we could say the Jacobian is the derivative. I mean, in that, writ large, broad brushstroke, fundamentally, what should a derivative be? Strong case can be made. Jacobian matrix is what a derivative really is of the multivariable function. None of this, I want to play pretend for a moment, and let's pretend a bunch of variables are constant. Partial derivatives they're derivatives where I ignore a bunch of realities. Right? It's kind of fake. Really, if you think about it, I'm just going to pretend. I've got all these different input variables. I'm going to pretend they're all constants, except for this one. Right? It's kind of a make-believe, artificial construction. This is highly general, highly natural. This is, by the way, again, not just my little personal point of view. This is sometimes the Jacobian matrix is referred to as the derivative matrix, because it is the derivative, again, ultimately, very naturally, the derivative of this kind of a multivariable function. Anyway, I'm a big believer in this point, so please try to digest. Now, here's something we can do with this. Oh, come on. Pen. There we go. Something really nice we can do with this. We can take a different interpretation on the matrix form of the chain rule. Now, the matrix form of the chain rule, again, I initially presented this as a kind of a bookkeeping tool that, this formula for matrix multiplication, it just happens to be then that you can, instead of writing down 16 different formulas, this one algebraically convenient shorthand does all of it for us. Again, algebraically, that's nice. But we encountered this as a bookkeeping tool. Now I want to show you a geometric perspective on why this is geometrically natural. And this is geometrically natural using this point of view of thinking of Jacobians as relating input velocities and output velocities. And this is actually ultimately a pretty straightforward argument, but let's consider these scenarios where I've got first this function g that gives y variables as functions of x variables. And now secondly, suppose I have a function I'm going to compose it with, this function f, where the z's are functions of the y's. And we're going to compose in the usual way. Right? The composition gives the z's as functions of the x's. Right? Okay. Here's some obvious things that I can write down. I mean, simply interpreting, what does the derivative of g do? The derivative of g is the thing that you multiply by x prime to get y prime. And we just wrote that down on the previous page. It's the relationship between input changes and output changes. Those are x prime and y prime, respectively. Okay. Well, what does the derivative of f do? The derivative of f relates y prime and z prime. So the derivative of f is what you multiply by y prime to get z prime. Okay, well, and it remains that the derivative of the composition is what you multiply by x prime to get z prime. So we've got these three sort of, this little diagram of what multiplies by what to give what. I know multiplication by jg turns x prime into y prime, and the multiplication by jf turns y prime into z prime, but I know that multiplication by the Jacobian of the composition turns x prime into z prime. Well, that automatically tells you then that just because multiplications multiply, that these matrices these two matrices have to be equal. The product of those two matrices has to equal to that matrix. Because multiplication first by jg followed by multiplication by jf accomplishes exactly the same thing as just multiplying by the Jacobian of the composition in the first place. Right? And so, therefore, that these matrices are the same. So I think this is a really, really nice point of view. Again, my just feeling, personal opinion. But this, the matrix form of the chain rule. Again, what we saw as a bookkeeping shorthand here, right? That bookkeeping shorthand has a very natural geometric interpretation about, look, if you've got velocity vectors all over the place that are related by way of these functions and individually by multiplication by derivative matrices, unavoidably, these derivative matrices have to multiply. I think that's really nice. Okay. All right. Alrighty. I want to talk about second derivatives. Second derivatives are a little bit weirder in a multivariable context as pertains to the chain rule. We'll start off with a real straightforward, immediate thing. If z is a function of x and y, if x and y are functions of r and theta, and by the way, this is a classic example that you'll notice that the formulas I have here for x and y as functions of r and theta, that's just polar coordinates. Right? If you haven't seen polar coordinates before, we're going to spend some time talking about this later. But anyway, we're going to do this as algebraic here for the moment. But it's a classic example. So if you have this composition, then you can reasonably ask what is, for example, the derivative of z with respect to r. And, well, there's two different paths. There's the path through x, and there's the path through y. And so there's your chain rule. And some of these things are easy to compute. Partial of x with respect to r, well, that's cosine theta. That's an easy calculation. Partial of y with respect to r, likewise, sine theta. Right? So, no problem starting off. One little slick move that I'm going to do here, I am going to rewrite what I had initially written in Leibniz notation. I'm going to write in a sort of that more Newton-like notation. This is going to have some advantages momentarily. But anyway, there you go. It's just a rewrite. So here's our formula for the first partial of z with respect to r. What if you want to take a second derivative? Okay. Go ahead, I suppose, right? You can just kind of, don't we have formulas for these kinds of things? What is there to talk about? The weird thing is that at some point you're going to find yourself wanting to take a derivative of zx. And you're going to be thinking to yourself, okay, wait a minute, well, what is the derivative of zx, for example, with respect to r? Is it zxr? Can you do that? Does it make any sense? It kind of doesn't, as it turns out. So let me just point you in the right direction, the way to think about this. The point is that because z is a function of x and y, and just think literally, think symbolically. If z is some expression that involves x's and y's, what happens to it when you take a derivative with respect to x? this expression involving x's and y's, if you take an x partial, it's going to turn into some other expression involving x's and y's. Zx is also a function of x and y. That's just an algebraic appeal. Yeah? So my suggestion, and this is not in the book, but I think this is a really good idea, because Zx is a function of x and y, and it will need to be treated as a function of x and y, it should be indicated on your diagram that it is a function of x and y. So append your diagram. Again, I don't know, the book doesn't make this suggestion, but I think this is really, really helpful. Don't just sit around and operate, with this that you started with. This Zx is a function of x and y. This Zy is a function of x and y, and append accordingly. And then now it's just a matter of going sort of slowly and carefully and just, I guess I'm out of time. Shoot. But having this like this is going to make it easier for us to take this next step on Monday. So we're out of time. See y'all later. Don't forget to turn in your homework. And if you came in after I checked attendance, make sure that I get you down